Swayam Prabha. Digital India. Educated India.
Fluid statics refers to the condition where fluid is stationary, there is no flow. Now, typically, fluid statics is referred as hydrostatics, but hydrostatics is more appropriate for analyzing static conditions for water. In fact, it's a loosely used term where even for atmosphere it's sometimes referred to as hydrostatics, but it's actually fluid statics. So fluid statics can be broken up into two major parts. The first one is manometry, that is the measurement of uh, pressures, and the second is forces on submerged bodies and the forces acting on partially submerged bodies, that is bodies which one part of it is submerged and one part of it is above, like ships, and the stability of such bodies. Yeah, okay. So hydrostatics will be split logically into manometry, and the other will be forces on submerged and partially submerged bodies. So manometry is very important from the point of view of measuring pressures, and these topics are very important for designing of ships, floating objects, and so on. And both these topics, so today we'll try to cover manometry. So, okay, yes.
The screen is not visible.
Screen is not, oh, I have not shared my screen. देखो तो, my bad. My bad. It happens when you have classes so early, such things happen. Now?
Yes, and now visible.
Acha. And I request you to please stay on mute and message me if there is something wrong. Okay. Acha. How do I mute everyone?
In participants tab, there should be a mute all option.
Ah, yes, yes. Mute all. Okay, guys. Let us proceed. I'll open up the session for discussion, so you can ask all your questions there. So let us begin with the first idea, that of pressure at a point. In order to find the pressure at a point, we will consider a fluid wedge like this. Let the length of this wedge be delta x, let the length of this side be delta y, and length of the slant be delta s. Now we know that pressure, it always acts normal to the face, and it is compressive in nature. If that is the case, the pressure on this face will be this, and let us call it px. The pressure on this face will be py. Similarly, the pressure on the slant face will be normal to the slant face, and this pressure, let us call it p. If the angle of the wedge is theta, like this, so we can write down that this particular angle will also be theta, and we will require this in order to find the components. Let us perform a force balance on this particular wedge, given that the wedge is in equilibrium. So wedge is static. So x direction force balance. So because we are considering a two-dimensional object, the width into the paper can be assumed to be b. So b is the width into the plane. We could have also chosen it to be 1. It makes no difference. So in the x direction, we have px multiplied by the area over which px is acting. So px is acting on this face. So the area of that face is delta y times b. Py is acting on the lower face, but that comes in the y direction balance. On the slant side, we have minus p times the slant area. So slant area will be delta s multiplied by b. But we have to take the component of this particular force in the x direction, and that particular component will be the sine component, because theta is this angle. So this will be 0 in order to maintain a static equilibrium. In the y direction balance, we will have py times the area over which py acts, which is delta x times b, which is this base area, minus, so the force due to this pressure acts in the negative y direction, so that will be p delta s b, but now the cos component of this particular force. And apart from this, we have the gravity of the fluid element acting downwards, because we assume that g is acting in this direction. So the mass, so this will be minus half delta x delta y times b times rho. So this entity is the mass, because half delta x delta y times b is the volume of this entire wedge, times rho will be the mass, because mass equal to density times volume, and this will be multiplied by g, and this will be equal to 0 for the condition of equilibrium. Let us simplify these expressions by making use of trigonometry. From this particular trigonometry, we see that delta s cos theta will be equal to delta x delta s sin theta will be equal to delta y, and these follow simply from trigonometry, because this is delta y, this is delta s, and the projection of delta s on the x-axis is delta x, and that projection is the cos theta. So we can first of all cancel b from these two terms. We can cancel delta y with delta s sin theta, because that relationship follows from trigonometry, and this relationship yields us px minus p is equal to 0. Now what about this particular relationship, the y direction force balance? We can first of all cancel the unit width or the width from all terms, and let us divide everything by delta x. So naturally this term cancels. Now delta s cos theta and delta x, they cancel out, and this delta x also cancels out. So in the end we are left with py minus p minus half delta y rho g is equal to 0. Now because we are interested to find out the pressure at a point, we must shrink the dimensions of this wedge to a single point. And the way to shrink is while maintaining geometric similarity. So if this is the fluid element, I must let delta y and delta x go to 0 in such a way that I still maintain the angle between the slant and the x-axis. It has to go to 0 in this. It cannot go to 0 in an arbitrary way. So, however, in this case, it does not matter. Delta x and delta y both go to 0. And if that goes to 0, this term is devoid of any delta x and delta y. Similarly, this term is devoid of any delta x and delta y. This term is devoid of any delta x and delta y. Only this term contains a delta y, and this term will consequently vanish. As a result of which, from the y force balance, we obtain Py minus P equal to 0. So if we combine these two results, we have Px equal to Py is equal to P, which means that the force at a point does not depend on which direction it acts from. It means that the force due to pressure at a point is isotropic. It acts equally from all sides. Okay, so extending this, I can draw all the other lines of pressure at a point. At a point, they are all acting equally from all sides. So they are equal, and they are not just equal, but they act equally from all sides. So pressure is said to be isotropic. So far, we have considered the pressure acting at a point in the fluid, but now let us consider the forces acting on a fluid element because of the action of pressure. For that, let us draw a fluid element in the form of a cube. Consider this fluid element and this length delta x, this length delta y, and this length as delta z. So delta x, delta y, delta z are the lengths of the differential element. On this object, we will consider pressure acting on this face and pressure acting on this face. The pressure acting on this face will be the pressure acting on this particular face, if we call it as P at x, y, and z, meaning it is the pressure at this particular location. Consequently, the pressure at this particular point will be P at x plus delta x, comma y, comma z. Because the y and z coordinates have not changed, all that has changed is the delta x. And we are using here the field description of P, which we have already discussed at great length during the discussion of a fluid continuum. So pressure is a field variable. So then let us now perform a force balance in the x direction. From the left face we have P at x, y, z multiplied by the area over which the pressure acts, which is delta y, delta z. From the right face, it will be minus of P at x plus delta x, y, z, and it also acts on a fluid element delta y, delta z. And this is the force. So let me call it as dfx. Now I can write this as P x, y, z minus P x plus delta x, y, z times delta y, delta z. Now from Taylor series, we know that P at x plus delta x, y, z can be written in terms of P x, y, z plus del P del x at x, y, z times delta x plus 1 upon 2 factorial delta x square del 2p del x2 at x, y, z plus order delta x cube. So this follows from the Taylor series. So if we rearrange this, we have p x, y, z minus p x plus delta x, y, z is equal to minus del p del x delta x minus delta x square by 2 factorial del 2p del x2 minus order of delta x cube. So I have simply taken this term on the right hand side and all the other terms apart from this term on the left hand side. Essentially I have arrived at this. It's a very simple manipulation. And thus we obtain over here, if you substitute this particular expression, we will have minus del p del x delta x minus delta x square. So minus delta x square times something. All the other terms will be higher powers of delta x square. This multiplied by the area that we had taken out. So then this becomes minus del p del x times delta x, delta y, delta z minus delta x square, delta y, delta z times the other terms, higher order terms. Now delta x, delta y, delta z can be identified as delta V, that is the volume of the fluid element. So let us divide everything by the volume. So dfx divided by the volume, okay, this will be minus del p del x minus, so delta x, delta y, delta z, this entire thing is multiplied another delta x, so this will be delta x times everything. Now d capital Fx upon dv delta V is the force acting on this fluid element per unit volume of the fluid element, and we will call this force as d small fx. So the small fx will be representative of a force per unit volume, and this will be equal to minus del p del x minus delta x times the other terms. Now as we shrink the size of this fluid element, that is, we let delta x go to 0, delta y go to 0, delta z go to 0, this particular term cancels out. So essentially we are trying to find out the force due to pressure on a differential element, and this gives rise to dfx is equal to minus del p del x. By similar construction, we can show that dfy will be equal to minus del p del y and dfz will be equal to minus del p del z. Now I can write df, that is the body force acting on the fluid element, as dfx I plus dfy j plus dfz k. Equivalently, I could have written it as dfx ex plus dfy ey plus dfz ez. So it's just a convention of using the appropriate unit vectors. So then let us expand this particular term. So it will be del p del x I minus del p del y j minus del p del z K. And if you look closely, this is actually minus of del P del X I plus del P del Y J plus del P del Z K. This is nothing but minus of the gradient of the pressure. Therefore, the body force acting on a fluid element is minus gradient of pressure. So we have obtained that the body force is equal to the minus of the gradient of the pressure. But what is the physical meaning of this particular minus pressure gradient? And it will pop up at quite a few places throughout our study in fluid mechanics. So it is worth looking into the physical interpretation of the negative pressure gradient. Let us consider a simple one-dimensional problem. So this is the x-axis, and suppose this line is x equal to 0, this line is x equal to 1, this line is x equal to 2, and this line is x equal to 5. Let the pressure at this point be 100 Pascal. Let the pressure over here be 80 Pascal. Let the pressure over here be 30 Pascal, and let the pressure over here be 60 Pascal. Now let us consider the first cell, that is the region between x equal to 0 and x equal to 1. Because it's a one-dimensional problem, this particular expression minus gradient of P will simply become minus dP dx in the I direction. So in the first cell, let us find out what dP dx will be and what minus dP dx will be. So what will be dP dx? It will be the value of pressure at 1 minus value of pressure at 0 divided by 1 minus 0. So this is a simple forward difference. Everyone has done this in their first year. And so this becomes 80 minus 100 divided by 1. This is minus 20. So if this is minus 20, minus dP dx will become equal to 20. And so the body force is 20I. So the force in this particular cell is acting in this direction and the magnitude is 20. What about cell number 2? So in cell number 2, it will be P at 2, which is 30, minus P at 1, which is 80, divided by 2 minus 1, which is 1. So this will be equal to minus 50. So minus dP dx will be 50 and dF will be 50I. So this is cell number 2. What about cell number 3? In cell number 3, it will be P at 5, which is 60, minus P at 2, which is 30, divided by 5 minus 2. This is equal to minus 30 divided by 3, so minus 10. Oh, sorry, this is not minus 30, this is 60 minus 30 will be 30, divided by 5 minus 2, which is 3, and this will be plus 10. But the negative pressure gradient will be minus 10. I just multiply this by a minus sign. And so the force will be minus 10I. If I draw, so if this is 20, so the force in the second cell was 50. It was larger than this. So this is 50. And in the third cell, it is minus 10. So it is something like this. So it's 10 but pointing in the other direction. So what is our interpretation? Minus gradient of pressure is showing me the direction from higher pressure to a lower pressure. And larger the difference in pressure across space, the larger will be the force. Over here, the force is pointing in this direction, and it is the direction of decreasing pressure because we are going from 60 Pascal over here to 30 Pascal over here. So the interpretation is very clear and it is very simple. Minus gradient of pressure indicates the direction from higher pressure to lower pressure. And it is sort of an indication of how the force is acting upon a given object. So if you consider a piece of paper like this, or not like this in particular, like this isometric view, if you blow on the paper from this direction, essentially you are creating a higher pressure over here and lower pressure over here, which causes the paper to flap in this direction. So it is the indication of the direction of the force acting on the fluid element. So if you have in general a pressure gradient like this, so let me draw a few isocontours. So isocontours are line. So contours are line which join equal values of pressure. So this is an contour of P equal to 100. So the contour is also called as an isoline. So isoline meaning iso means constant and line is line. So it's a line which has constant pressure and that pressure value is 100 Pascal. This is 80 Pascal. Then suppose this is 70 Pascal. Then suppose this is 60. Suppose this is 50. So the direction of the gradient will be orthogonal to the contours. It will be orthogonal to the isolines. So it will be something like this. I mean, it's not very accurate, but you get the idea. Okay. It will be always orthogonal to the isolines or the contours. Okay. That is the property. So minus gradient of P is orthogonal to iso P lines, also called as isobars, and the direction of this particular vector is from high pressure to low pressure. That is the interpretation of the gradient. In this segment, we will see how to make use of a computer to plot the isolines of pressure and the negative gradient of the pressure. So first of all, let us clear all the variables and clear the screen. Now we will define a domain from x0 to 2 pi, and let us say we have 20 points in this, and let us define the y extent going from 0 to 2 and say we have 15 points in this. Now we will make a mesh grid out of this. So this is the command, and you can easily look it up on the internet, or I have put up a bunch of videos through a separate NPTEL course on my YouTube channel. It was a part of the assignment, or rather supplementary videos. and you can easily learn how simple functions of GNU Octave. So this particular software is called as GNU Octave. It's the free alternative to MATLAB. It has all the functionalities of MATLAB that you would want, and it's free. The most important thing is it allows you to exchange. If someone has MATLAB codes, it allows you to directly use those MATLAB codes in the environment of GNU Octave. So it's quite portable. So anyway, let's proceed. So capital X and capital Y will now contain the information of the mesh grid, which is the two-dimensional grid spanned by X equal to linspace so and so and Y equal to linspace so and so. Excellent. Let us define a certain P. So let me just define it analytically as exponential of minus Y dot star sine of say X. Okay. So now let us visualize what P is going to look like. So I will make use of a pseudo color plot. So let me write figure 1, P color this, X label X, font size 18. Let me copy this. So Y level will be Y and the font size will also be 18. Set GCA font size 18 is just to make it look slightly larger. So let me run this entire thing and let us see how it looks. Very nice. So the pseudo color plot, it does show something, but we don't want these grids to appear. Fine. Let us make the shading interpolated, and this should make, yeah, so it makes the grids go away. Let us make the axis tight. Okay. Oops. So there has been a small typographical mistake. This should be level, and most likely this would have been coming up. Yeah, yeah, there would have been an error coming up, but CLC was running out of it. Anyway, so in this particular segment, we are going to use GNU Octave, which is a free alternative to MATLAB, in order to plot a certain isolines of pressure and how the negative pressure gradient looks on a vector plot. So in the environment of GNU Octave, let us first clear all the variables and clear the screen. Let me define the domain extent. So X will be linspace, which is a linear space going from 0 to 2 pi. And let's say I have 20 points. Let Y go from linspace 0 to 2, and let's say it has 15 points. Let me now define a mesh grid which spans X and Y. That is a two-dimensional grid from the X and Y ranges that we have defined above. So that will be mesh grid X comma Y. Let me now define P as an analytic function analytical function of x and y, capital X and y. So let me write it as sine of x times exponential of y. Let me now do a p color plot, which is a pseudo color plot. So let me define it as figure 1, p color x comma y comma p, shading inter, meaning the interpolation between each cell will be uh, a linear interpolation. It won't be flat. There are other options for making the shading, and I'll show you. So then let us put the x label as x font size. Let us make it 18. Let me copy this, paste. For the y label, it's just to make it look larger, nothing else. And set GCA, which is get current access, font size 18. Okay, let me run this by pressing F5, and there you have it. In this particular domain, which spans from x equal to 0 to 2 pi, which is 6.28, y varies from 0 to 2. The pressure over here is higher. Okay, so how do we know that pressure here is higher? We need some numerical values. So let me drop in the color bar, and in fact let me make the axis tight to remove any white space, and let me change the aspect ratio of the figure so as to make it look more reasonably scaled. D aspect, which is the aspect ratio of the figure, it should be 1. Okay, let me hit F5, and this is the plot that we have. So the yellow color corresponds to a higher pressure than the violet color, and we expect that the lines which show the negative pressure gradient, that is the force acting on a fluid element, will point from the yellow zone to the purple zone. Let's find out. Okay, before finding that out, let me just show you the different interpolations. So shading flat creates this. This is the flat shading, and if I don't write anything, it will create the default cell shading. It shows the cells also. Okay, but for me, it doesn't matter. For this particular example, it doesn't matter. So let me define the gradient of the pressure as Px Py will be gradient of P comma dx comma dy. So gradient is an inbuilt function in GNU Octave which takes input as the scalar field P and the delta x and delta y of finding out the gradient. So dx will be x2 minus x1. Similarly, dy will be y2 minus y1. In fact, dx and dy could have been any index minus the previous index. That is, it could have been x23 minus x22 or y19 minus y18. It doesn't matter. Okay. So dx and dy could be anything as long as this whatever you choose here is within this particular range. You cannot exceed that range. It will throw an error otherwise. Okay, fine. So px and py are defined. Let me say that okay, I want to draw whatever I'm going to draw on figure 1. Let me hold all. Quiver is the name of the function which helps you to make vector plots, and now the directions are not going to be pressure gradient, but it should be the negative of the pressure gradient, so it should be minus px minus py. In fact, let me make the lines red. All right, let me run, and excellent. Let me enlarge this. So from the yellow zone to the violet zone, there is a flow, and these arrows are directions. In the beginning of this segment, I had said we'll draw the ISO lines, but instead I ended up drawing the P color. So let me comment out the P color line. Let me go to the next line. Let me say I want the contours. So contour x comma y comma P, but now maybe say I want 20 contours, so I just put 20 contours. If I run this, and boom, I have here 20 contours of different values of the pressure and the corresponding negative pressure gradient. So this is how it looks like. In fact, I can make the contour filled as well. I just have to do contour F, which is a function to make a filled contour. It looks slightly more better. In fact, if we have less number of contours, so let us say we have 5, it looks much better. It looks quite easy to understand. So this entire region is like at a pressure of 4, this entire region is at a pressure of -6, and so on. Okay, so this is how we are able to show the different things with the help of a computer, and that too not a commercial software. Let us now move to the equilibrium of a fluid element. In the earlier section, we have looked at the body force acting on a fluid element because of the pressure, and we saw that it's a negative of pressure gradient. But now we want to look at an equilibrium of a fluid element. In order to find the equilibrium, we must now account for the other body force acting on the fluid element, and that other body force is its own weight. So let us consider the body force due to gravity. So it will be the density times its volume, delta x, delta y, delta z, times the g vector. Now the g vector points downwards, but we will write it at the time being, for the time being, as a vector. So d small fg, which is the body force given that this is the force. So it is the force per unit volume, will be simply rho times g. So the total force acting on the entire fluid element will be the total of the force acting because of pressure plus the force acting because of gravity, and d small f on the fluid element is equal to d small f p plus d small f g, and this is equal to minus of gradient of pressure, and this particular term is plus rho g vector. And at equilibrium, this thing will be equal to 0. So let us write the three components of this particular expression. So in the x direction, we have minus del p del x equal to 0. In the y direction, we have minus del p del y is equal to 0, because see, g has only a component in the z direction. So in the z direction, we have minus del p del z plus rho times the g vector, but g vector itself points in the negative z direction. So in fact, let me show you how to properly rigorously write this. Minus gradient of p, the components are actually minus del p del x I, minus del p del y j, minus del p del z k. So if I collect the k components of this particular expression, I will have minus del p del z minus rho times g equal to 0, because g vector is nothing but minus g times k. So it's essentially k pointing in the minus k, it is fundamentally G pointing in the minus k direction. So if you equate this to 0, it means the inside component of the k vector must be 0, and that means minus del p del z minus rho g is equal to 0. What is our understanding from the fact that minus del p del x is equal to 0 and minus del p del y is equal to 0? Both of these imply that p cannot be a function of x and y, but p must be a function of z. Okay, so if this is the z direction, this is x and this is y. At a given z location, so this fundamentally means that at a given z location, my pressure, it does not depend on the xy coordinate. It is constant across all x and y coordinates. Okay, and this implies that we can write this partial derivative as an ordinary derivative. So del p del z becomes dp dz, and we have minus rho g equal to 0, and thus dp dz is equal to minus rho times g. This is the ordinary differential equation which governs fluid statics. Okay, so we have obtained minus, or rather dp dz is equal to minus rho times g. So let us consider a coordinate system like this, where this is the origin. So this is the origin at z equal to 0. Let us call the pressure at the origin as P0. So P0 can be the atmospheric pressure. Okay, in typical cases, we can consider it to be the atmospheric pressure. So let us integrate this equation along z. So dp dz integration from z equal to 0 to some arbitrary z. So if we want to integrate it to some arbitrary z, the inside z's must be set to a dummy parameter of integration. I cannot keep both of them z. Okay, this has been taught to you in class 11, 12 or something. And so this will be minus integration of rho g dz prime, where z will now vary from z equal to 0 to some arbitrary z. This particular integration is quite trivial because dz can cancel out, and it's simply an integration over dp. So it's simply integration dp from z equal to 0 to z equal to z. This is equal to minus integration of rho g dz prime. So this is p at z minus p at 0, which we call as p naught, is equal to minus integration of rho g dz prime from z equal to 0 to some arbitrary z. Now we cannot directly integrate this because we do not know whether rho and g are varying with z or not. So as a first assumption, assume that rho and g are constant. Under that assumption, we have p as z minus p at 0 is equal to minus rho g z minus 0. So essentially it becomes z. So this is the expression for the pressure at a given z relative to the pressure at z equal to 0, which we denote as p naught. And if p naught is the atmospheric pressure, then pz minus p atmospheric is equal to minus rho gz, and the difference between the pressure at a point and atmospheric pressure, that is how large this particular pressure is relative to the atmospheric pressure, is called as the gauge pressure. We can similarly define the vacuum pressure So the vacuum pressure is how low below the atmospheric pressure a given pressure is. So P atmospheric minus Pz, if I were to write it like this is called as the vacuum pressure. So how low relative to the atmospheric pressure is our pressure. So now we have an expression for the pressure at a point. In particular, we have an expression for the gauge pressure. Let us look at the justification whether G and rho can be assumed as constant. So the radius of the earth is 6,400 kilometers. So suppose from this point at the surface of the earth, you go to an altitude of 20 kilometers, which is like the service ceiling of some supersonic jets. So the radius has changed from 6,400 to a radius of 6,420, and gravity, we know it varies as 1 upon r square. So G, so if I call the gravity at the surface of the earth as G naught, so G naught upon G is equal to 6420 square divided by 6,400 square, and this is actually a very small number. So if you actually do the calculation, G naught minus G upon G naught, which is the delta G upon the G at the surface of the earth, you will see that this is actually a very small fraction. And let me just pull out my calculator, my old trusty calculator from 18 years back. It is 6400 right, 6420 square minus 6400 square is divided by 6400 square times 100. So it actually comes out to be 0.625%. So this is a percent, it's not even the ratio. The ratio is 6.25 10 to the power minus 3. So gravity can actually be, the variation of gravity can actually be neglected in these calculations. Now similarly, effect whether density is constant. So density, we know that there are two aspects to it. The first aspect is density in a fluid. Second aspect is density in a gas. Okay, let us see whether the density changes with depth. So the most saline water is found in the Dead Sea. Salinity, because of the salinity, the density becomes something like 1100 kg per meter cube, while that of fresh water is 1000 kg per meter cube. So it's a delta rho of 100 over a value of 1000. So it's still not a large. Actually, this is. I have to check the value of salinity of extremely salty water. But if you check the calculation, that number is also going to be a very small. The fraction is also going to be a very small number. Okay, it varies something like 1013 over 1000. So if you add a lot of salt to just fresh water, this is not the correct value. If you add a lot of salt to fresh water, you will get a value of 1013. So it also leads to a very small variation of density with the addition of salt and all these things. So even with depth, saline water at the depths of oceans and all, the density does not change a lot. The pressure changes, but the density does not change. But what about gas? So gas, the pressure and the density are related through the equation of state. They are related through the equation of state, meaning that if I write down dp dz as minus rho times g, this particular rho for a gas is actually a function of pressure. So P equal to rho RT, where R is the universal gas constant for that particular gas. It is R universal divided by the molecular weight of the gas. So if this is true, then we have dp dz is equal to minus P G upon RT. This implies dp upon P is equal to minus G dz upon RT. So let me integrate this from points 1 to 2. So this will be ln P. So let me call the other point as P and the original point as P naught. So ln P upon P naught is equal to minus G Z minus Z naught upon RT. And this is under the assumption that the temperature itself does not change with Z. Okay, I hope you can appreciate this, that temperature is assumed to be a constant. So this, if we set the value of Z naught to be 0, so then we have ln P upon P naught is equal to minus Gz upon RT. So P equal to P naught exponential of minus Gz upon RT. So if we do not assume the ideal gas relationship between density and pressure, the relationship that we would have obtained is P equals P naught minus rho G Z. But because of considering the implicit dependency of density on pressure, rather the explicit dependency, we have an exponential decay in the atmospheric pressure as opposed to a linear change. Okay, so that pretty much wraps up this particular lecture on the fundamentals of hydrostatics. Yeah.
How good is this assumption?
How good is the?
Like, how much is the error in this P equal to P naught?
That will be the assignment. That will be assignment. Okay. And the assignment will also contain a problem in which the temperature will not be a constant. We all know that the temperature actually varies over the surface of the earth from say 20 degrees Celsius to minus 11 degrees Celsius, not minus 11, minus 60 degrees Celsius over a range of 11 kilometers. So inside our troposphere, so this altitude of 11 kilometers is like the troposphere. Then it remains constant for a while, after which it increases slightly. So the slope of this, it is called as the lapse rate. It is like the slope of the temperature curve. So temperature goes from T naught at the surface minus beta times Z. So this is called as the lapse rate. So we conclude our video over here, and I'll be back next time with partially submerged bodies and stability of floating bodies. Until then, farewell. Bye.